Good afternoon, everyone. Welcome to the special topic of today. And today I will give you a taste of, if I find my presentation, where is it? Sorry, just a second. I think I just lost it. Here we go. Sorry, it was on the last page. Just a second. Where is it? Sorry, I have too many open windows here, it seems. Come on. Sorry, I think I need to stop and share again because I don't find it. Google Chrome, find. Here we go. Sorry. I don't know. Okay. So let us start now. And my special topic of today will be a very brief introduction to quantum computing. Yeah, probably some of you might have heard about quantum computing in the past, or by just looking at the newspapers. Yeah, and I just want to give you a taste of it. Yeah, and the plan of my lecture is that I will spend a few minutes of generic introduction, because some of you might not know anything about quantum mechanics. I will speak a few minutes about basic background in quantum mechanics, and then I will try to share with you why people are so excited at the moment about quantum computing and regard it as a potential future for high performance computing. Yeah? And on Thursday, one of my students will give you a half-an-hour introduction to Qiskit, which is a special, let's call it a special Python module to do quantum computing on your laptop or on a real quantum computer. Yeah. So this is the plan. So if pay attention today, on Thursday, after Thursday's special lecture, you should be able to write a simple quantum computing code. Yeah, today I won't use a word of Python. Yeah, we will leave it then for Thursday. Yeah, so you know, the history of computing goes essentially hand in hand with advances in artificial intelligence and machine learning. Yeah, the reason why things like ChatGPT are so successful is because we have GPUs that are very efficient at solving part of the problems related to machine learning. Yeah. And I want to start with this slide because we know already today that some special quantum computing devices are also good at solving some parts of machine learning calculations. Yeah? So that the worst case scenario for quantum computing is that there will be special devices like ASICs, FPGA, or GPUs that have something to do with quantum. Yeah. The best case scenario is, of course, that a quantum processing unit will one day replace the CPU. Yeah, the classical CPU that is at the core of all your PCs, phones, whatever. Yeah, cars. Yeah, yeah. So that is the final game. Yeah, but the worst case scenario is already good enough. Yeah, so that's why there is no harm in learning about quantum computing. Yeah, the worst case scenario can't be that bad. So when people, lots of people spend time thinking about the future of computing. Yeah, and you know, the traditional computing is based about the manipulation of bits. Yeah, and bits, as you know, is the mathematical foundation of the unit of information. Yeah, so classical computers operate with bits. Yeah. Some people believe that, you know, we need to take inspiration from how our brain works, yeah, and promote something that you could call neuromorphic kind of computing, yeah, and that is just combining biology with information. Yeah, what I want to speak to you today is that what happens if you combine physics with information. Yeah, the qubit is a physical system. Yeah, you can think of it as a small atom with two levels. Yeah. and looking at information in terms of quantum objects, like small, tiny little atoms, changes a little bit the games of the rules. And in fact, it changes them quite dramatically. And that's what I want to give you today, a taste of what changes and what is possible. So the reason why this story started in the last century, we can say today, maybe at the end of the last century, from the 70s onwards, is that quantum mechanics and information science started to merge into one discipline, that some people call quantum information science. And quantum information science has essentially three big pillars. There's quantum computing, there's quantum communication, and there's quantum sensing or quantum metrology. I won't speak at all about metrology, sensing, and communication today. I just want to give you a taste of the computing part. Historically, this is important because every time you open a newspaper or watch a TV news program, somebody mentions the fourth industrial revolution. And that's because from the 1700s onwards, there was a series of industrial revolutions. Over the last 2 centuries, but we also witnessed a quantum revolution, which started just at the beginning of the 1900s, with people like Max Planck, Albert Einstein, that developed the theory of what we call now quantum mechanics. That was motivated by observations that people couldn't explain using classical Newtonian physics, and so they had to come up with something new. And around 40 years ago, the experimental technology allowed us for the first time to manipulate single quantum objects. Like to manipulate one atom, to manipulate one ion, to manipulate one electron, and that opened up a second quantum revolution, where people really managed to manipulate quantum objects in the most quantum state to do things. We all know every table is done of atoms, but you don't really exploit a single atom from the table. But now we have that ability to exploit the properties of a single atom to do things, or series of single atoms to do things. And some people believe now that in order to achieve the full goals of the fourth industrial revolution, that we will have to combine the second quantum revolution with the fourth industrial revolution, and see what happens. And and if the first quantum revolution already gave us significant technological advances like the laser, diodes, transistors, the second quantum revolution gives us, as I mentioned, quantum metrology, quantum communication, which allows very secure transmission of data, and very fast processing of data in the form of quantum computing. So in order to get you excited about this, I need to go back in history and start with the first quantum revolution. And it all began, in a little bit not too serious way, with this gentleman, that you might know, at least the guys of you who like engines, from the Cardan joint. So he was quite a character, but he was not only interested in mechanical gadgets. He is also the person who came up with the famous eye, the imaginary unit. And because he was a professional gambler, that's how he earned his living. He also wrote one of the first books on probability theory. So not in the language that we use today. That came a lot later. But the reason why I mention it is because in order to understand quantum mechanics, we need both probability theory and complex numbers. Without those, it doesn't work. So that, I mentioned probability theory like we know it today was developed more or less 100 years ago by Kolmogorov. But that's not the topic of the talk. So what makes quantum mechanics really different? Did I start this? Yes. You see, here you see a typical quantum mechanical experiment. You have a source of electrons, one after the other, that hits a double slit, yeah, an object with two slits, and the electron can go to the right or to the left, yeah. So naively, you would expect that on the screen behind the double slit, you just see essentially two Gaussian peaks, yeah, one per slit, yeah. That's what would happen if you would throw tennis balls through the through the two slits, yeah. But if you do the experiment with electrons, and that is what is building up down in the lower half of the slide, yeah, you see that that's not what happens. Yeah? What happens is that you see a very typical interference pattern. Yeah, so that which means that electrons don't behave in this case like particles. Yeah, they behave more like waves. Yeah, this is what you would expect if you throw two waves through a double slit. Yeah, that's exactly what you would expect. Yeah. So this is already a very funny property of quantum objects. Yeah, that sometimes they behave like waves. Yeah, so that quantum mechanics is different. Yeah, because what you see here would, in principle, be possible. Yeah. So how do we need to think about these quantum objects? Yeah, and how does it relate to probability theory? Yeah. So if you think of the electron, let's say or the photon, this yellow dot, yeah, and you send it to to a beam splitter, so an object that is half mirror and half transparent, yeah, you would expect that half the time it goes up and half the time it goes to the detector at the bottom. Yeah. So if you do the experiment again, it might go down, and if you do it many times, you will observe half the time it goes up and half the time it goes down. Yeah. So typical quantum mechanical probability relation. Yeah. So that you could think that quantum objects are essentially like coins, yeah, but that is not the case, yeah, because if you do the experiment twice, yeah, so you see we have our light hits a beam splitter and then a mirror and then it hits another beam splitter, yeah, and it goes up. And if you do it again, yeah, it might decide to go another way, but funnily it always hits the upper detector, yeah, so that definitely our electron is not, our photon is not a coin, yeah, because it might work for one, but the moment you have two, it doesn't work anymore, yeah, because you would expect another statistics classically, yeah. So that one way of thinking of it is that that the photon goes essentially through both possibilities, yeah, and only when you measure, yeah, you know where it will be, yeah. And this is another element of quantum mechanics that is a little bit funny, yeah, and that is the superposition principle, yeah, which is also a wave property, yeah, as you might remember from some first-year lectures in physics. Yeah? So, and this is the mechanism, yeah, where the bit becomes a qubit, yeah. So this is a property that the qubit has, that the qubit can be in a superposition state. So, and I need to look at the time because I see already spoken much longer than I wanted. Yeah. So what is really going on? Yeah. What is going on is the following. Yeah. In classical physics, if you do the experiment with a double slit with tennis balls, yeah, you have two probabilities to go through one probability to go to the higher slit, one probability to go to the lower slit, and the probability to hit the screen somewhere is just the sum of those two probabilities. Yeah? And the problem with quantum mechanics is that this axiom that the standard additivity axiom of probability theory doesn't hold anymore. Yeah, what we need to do there is the following. Yeah, we need to associate to every part, yeah, a complex number, yeah, an amplitude complex, which is called a probability amplitude. Let's call it alpha, yeah, alpha 1 and alpha 2. And the probability to hit the screen somewhere is the sum of these two, alpha 1 and alpha 2 squared, yeah, because alpha 1 and alpha 2 are complex, so it's their square that is a number, a real number, yeah, and in this case a positive real number, which is then interpreted as a probability, yeah. So this is how quantum mechanics work, yeah. So that you see, if you represent alpha 1 as a complex number, yeah, like an amplitude and a phase, yeah, you see that the probability on the screen has a typical interference pattern. Yeah? There's all of a sudden there is a cosine appearing, which depends on the difference of the two phases. Yeah. So this is one of the things of quantum mechanics. Yeah? So that essentially, if you want to understand quantum mechanics, you need to be aware of two rules. Yeah, one is that if things happen in sequence, yeah, the probability amplitude is just the product of the two probability amplitudes. Yeah, and if things happen on possibly alternative paths, yeah, then the total probability amplitude is the sum of the single probability amplitudes. Yeah? And in both cases, the probability yeah, that you get in our classical world to observe something is just the square of that alpha. Yeah? So that these are essentially the only two rules that you know to remember from quantum mechanics to understand in principle what is going on. Yeah? There is one further element that we need from quantum mechanics, yeah? And this is the most counterintuitive, if you want, which is called entanglement. Yeah, and one of the fathers of quantum mechanics, Erwin Schrödinger, who saw entanglement for the first time on paper, yeah, he defined it as the characteristic trait of quantum mechanics. It's really what distinguishes quantum mechanics from classical physics. Yeah. Other people like Einstein had really big difficulties swallowing this, yeah, and they thought that it defies how we interpret reality and blah 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 and blah blah blah. Yeah, but the fact is that okay, let me skip. So the intuitive idea of entanglement is a kind of a concept of a very high degree of correlation that you can't achieve classically. Yeah. So if, for instance, you have this quantum state in the blue dot that decays, what Alice and Bob measure will always be perfectly uncorrelated. Yeah, whether they are sitting next to each other, whether the one is in Stellenbosch and the other one is in Durban. Yeah, the result of the experiment will be always exactly the same and always perfectly anticorrelated. Yeah, and this is something that classically we can't explain. Yeah, but it turns out that that's how our reality really works. Yeah. And the fact that we know it now for sure, yeah, that Schrödinger was right and Einstein was wrong, yeah, is that in the 60s, John Bell came up with a method to test, yeah, whether reality is according to quantum theory or is according to the local realistic picture that we have of the world that Einstein and his colleagues were promoting, yeah. And it took another 10, 20 years, yeah, until we had the experimental verification, yeah. And it was these three gentlemen, yeah, Alan Aspect, John Clausen, and Anton Zeilinger, that got last year the Nobel Prize, yeah, for essentially for proving that entanglement is there, yeah, yeah, and it is a useful resource. Yeah, it's something that we can really use, yeah, and quantum computing uses all these crazy things of quantum mechanics to solve computational problems. Yeah. So let's see how that works. Okay, we still have another 10 minutes. Yeah. Let's see how it works. Yeah. So what exactly do we understand under quantum computing and more generally quantum processing? Yeah, is that we really want to store, process, and transmit information exclusively with the laws of quantum mechanics. Yeah. So you know, we are well familiar with the bits. Yeah, the classical units of information can be 0 or 1. Yeah, we want to make it quantum, yeah, somehow. Yeah, yeah, and the simplest quantum procedure is to replace the 0 bit by a two-dimensional vector 1, 0. Yeah, and to distinguish it from the 0 bit, we put it in this fancy angular bracket that is called a Dirac bracket. Yeah, and this 0, because it's the end of the bracket, yeah, it's called a ket. Yeah, and same for 1. We replace 1 with the two-dimensional vector 0, 1. Yeah, so these are our 2 qubits now. Yeah. And the general state of a qubit, because we see in quantum mechanics, there is something like the superposition principle, will be a linear combination of this ket 0 and this ket 1. Yeah, so the most general qubit will be alpha times 0 plus beta times 1. Yeah, because the qubit can be in a superposition of 0 and 1, which is classically not possible. Yeah. So you see, the qubit is a completely different object from the bit, yeah, because of this property of the superposition with a complex number, yeah. You can think of the qubit as a vector, yeah, as a vector that goes from the center of a sphere to the surface of a sphere, yeah. And every point on the surface of the sphere is a kind of a legal qubit state, yeah, with 0 being the north pole and 1 being the south pole, yeah. So this is, from this you already see that it's a completely different game, yeah. It's a completely different game, manipulating qubits and manipulating bits, yeah. Okay, let me maybe skip this. Yeah, what can we do with a qubit? Yeah, so I skipped it because I see we are running out of time. Yeah, if we want to manipulate a qubit, it turns out we can do it only with so-called unitary operations. But for this, let's say just with the help of 2 times 2 matrices that have some properties. Yeah, so for instance, if we want to negate a qubit state, yeah, if we want to implement a a logical knot on a qubit state, yeah, we need to represent the knot as a 2 times 2 matrix that operates on the 2-dimensional vector, like you see on the slide. So the knot of 0 will be the matrix 0, 1, 1, 0 times 0, 1, 0, which gives 0, 1, which is 1, yeah, and the same for 1. Yeah, so it's a completely different way of manipulating information. Yeah, so we are in a bigger vector space, if you want. Yeah, and similarly, there are whole arrays of gates, yeah, of quantum gates to manipulate the qubits. I just showed you the knot. There is a Y gate, a Z gate, there is a H gate, a Hadamard gate, which is a little bit special because that's the gate that can produce a superposition. So you see the Hadamard gate, if you apply to 0, it gives you a state which is a superposition of 0 and 1. Yeah, so those are things that can do. And together with and the basic idea, of course, is to build quantum computing into a quantum register, yeah, and that would be a collection of single qubits. Yeah. So, for instance, if you have a quantum register of 2 qubits, like in this example, yeah, you will be able to represent each of the 2 qubit states by a 4-dimensional vector. Yeah, so it goes with 2 to the power of n. Yeah, if you have n qubits, it goes with 2 to the power of n. Yeah. Okay. Then, of course, so far I only showed you manipulator of 1 qubit. Yeah, there are also gates that can manipulate 2 qubits. Yeah, and the most famous one is probably the C knot, yeah, that you see here on the left-hand side. So an identity in the first qubit followed by a knot in the second qubit. Yeah, so this is a conditional knot. Yeah, and this is important because it turns out, yeah, that in order to build a quantum computer, yeah, you need only to be able to produce a set of single qubit gates and 1 C knot. Yeah, if you can produce the single qubit gates X, Y, and Z, as I showed you before, and C knot in large quantities, yeah, you're in principle able to build a quantum computer that can solve any quantum algorithm. Yeah, so that's why those 2 classes of gates are very important: 3 single qubit gates and 1 2 qubit gate. Yeah, there are variations on the theme, but that's the core. That's the core idea. Yeah. So that altogether, quantum computing is just you prepare a register of qubits, you apply a set of quantum gates that are here represented by this collective U. You run the qubits through the gates and you measure at the end. Yeah, and according to the rules that I described before. Yeah, and you have to interpret to build the U such that the whole system solves a problem. Yeah, and building quantum computer is not very different from building classical computers, because you need the same kind of tools, although they are all different. Yeah, you need to have the algorithms, you need to be able to implement them on a circuit, you need a compiler. Yeah, once you have written the code, you need a compiler needs to bring the software on the machine, you need a processor to run it, and so on. So you have a complete full stack approach to quantum computing like you have for classical computers. Yeah? And over the years, and I see I need to slowly come to an end, lots of algorithms have been developed. Yeah? From the very simple algorithms from the early 90s, where people just found toy algorithm to show that in principle you could do something, to algorithms like where is it here? Sorry, I don't find like the Grover algorithm in 1996 that can solve the search problems much more efficiently than a classical algorithm. Yeah. So then and since then there is a whole website called the Quantum Algorithm Zoo, yeah, where there are hundreds, if not thousands, of algorithms listed by now. Yeah, so there are really large classes of models that are of algorithms that have been developed, from searching to machine learning and almost everything in between. Yeah. And okay, let me skip this one, just to give you a taste, yeah, because at the moment we don't have yet the fully fledged quantum computer. Yeah, many people are working towards that goal, but you can't buy it yet. Yeah, you can buy smaller quantum computers, and I will mention it just now. Yeah. There's a class of algorithms that is called variational quantum algorithms. Yeah? And what these algorithms do, they combine a quantum algorithm with a classical optimization problem. Yeah? And it turns out that this generic strategy is very, very successful. Yeah? So you can use it already to solve some problems in quantum chemistry, in optimization, and in various other classes of problems. Yeah? So that's what we can do today. Yeah. At the moment, we live in the era where we have NISC computers. Yeah? Those are noisy intermediate state quantum computers. Yeah. And in 2018, yeah, when this term was coined by John Preskill, yeah, we were envisaging quantum computers between 50 and 100 qubits. At the moment, companies like IBM and others are building prototypes that have a few more qubits than that. Yeah, but still, they don't have enough qubits to do error correction. Yeah, because even classical computers have error correction codes inside. Yeah, because there are always sources of errors. Yeah. But at the moment, we don't have the technical ability to build enough qubits to run next to the quantum algorithm, also the error correction. So it's essentially you can do quantum computing without a safety net. Yeah, so that's why these computers are called noisy. Yeah? But nevertheless, there's a kind of a race amongst the big company to prove some quantum advantage. Yeah? In a paper of 2019, Google and NASA claimed quantum supremacy. Yeah? But that's a term that not everybody likes. So in the meantime, people prefer to speak of quantum advantages. Yeah? And the original claim was that the quantum computer of Google could solve a problem in minutes that a classical computer would have solved in so many years. Yeah. These claims are then revised over time because both sides, the quantum and the classical, get better. Yeah, but anyway, there are examples where quantum computers can solve problems better than classical computers. Yeah? As I mentioned, there is a whole array of algorithms where we know that quantum computers will give us a speed up. Yeah, and you can see it, for instance, just looking at this slide, the two columns in the middle. Yeah, you see that the scaling with the complexity of the system of the classical algorithm compared with the quantum algorithm. Yeah, and on the quantum algorithm side, you see lots of square roots and logs. Yeah, yeah, which is much better than just powers of n. Yeah, so you see there are classes of problems, and the list could go on and on and on, where quantum algorithms, in principle, do better than classical computers. Yeah, and I think this is it from my side for today. And I think I just finished on the, on the dot. Yeah, I'm sorry that it was maybe a little bit fast. Yeah, but on Thursday, you will have the opportunity to go through this again in Python. Yeah, because one of my students, Ian David, who gave that presentation already a few times in other setting, will give you a quick demonstration on how to implement a qubit in Python on your laptop and in principle on a real quantum computer, just the same host code. You just need to send it to another backend. Yep. So that is the plan of the week regarding quantum for you. It might not be of immediate interest to all of you at the moment, but just keep it in mind, because maybe one day you will have to use it. Yeah. So thank you very much. And I don't know if we have time for some questions, or if you're all eager to listen to Uwe's presentation. I see Benjamin, please. What can I do for you?
Yes, Prof. Thank you for the presentation. I just wanted to know, can you maybe give some examples of different applications or cluster of problems that you would use a quantum computer over high-performance computer, maybe?
Yes. You know what? There are. I mentioned, for instance, a search and optimization. Yeah, that is an area where people have big hopes for quantum computing. Yeah, for instance, in big companies like NASA and Airbus, they use quantum computing to optimize the design of wings or rotors in their engines. Yeah, things like that. Problems that are really complicated. Yeah, or very complex scheduling problems can be easily become very, very complicated. Yeah, another obvious area of application for quantum computers is quantum chemistry. Yeah, and that is not surprising, because quantum chemistry is quantum. and quantum computers are supposed to be very good at simulating anything that is quantum. Yeah, so there are big efforts, for instance, to use quantum computing to design new pharmaceuticals. Yeah. Which is one of the biggest number crunching efforts at the CHPC, probably. Yeah? You can do that also with quantum computer. Of course, we are getting there because we still don't have the fully fledged quantum computers, but there are lots of startups working very hard to design new pharmaceutical and discover new medicine using quantum computing. Yeah? Also, along the similar lines is material science. Yeah. There are many companies that use quantum computing to design better batteries, for instance. Yeah, and you know that is a problem that, particularly in South Africa, is very acute. Yeah. And so on. The financial sector is very keen on quantum computing because of those optimization possibilities. Yeah, you know, you need to optimize complex portfolios. That's a very complicated optimization problem, and that's where quantum computing, for instance, can also kick in. Yeah, and there are many more examples. Yeah.
Thanks, Prof. Just one question I saw in the Zoom chat says, why is it difficult to build a quantum computer? What are the physical limitations?
Okay, that's very interesting. No, thank you very much for that question, Werner. The point is, you know, in order to do quantum mechanics, you need to use all those fancy properties of quantum objects. Yeah? Quantum superposition, quantum entanglement, and so on and so forth. Yeah. But the moment you build arrays that involve many qubits, yeah, they start to behave classically. They start to behave like your table. Yeah, you can knock it, and there is nothing quantum going on in there. Yeah, so the moment building a quantum computer means that you need to fight the quantum computer to become a classical object. Yeah, because there is another mechanism of quantum mechanics called the coherence. Yeah, which is the mechanism that explains sort of the transition from quantum to classical. Yeah, in the classical world, I would like to be in two places at the same time, but I can't because I'm not quantum. I'm a classical object. Yeah, and that is what kills then quantum computers. Yeah, so so you need to design the quantum computers and build them in such a way that you keep the quantum properties alive, and you avoid them becoming classical, because the moment they become classical, your quantum computer is useless. Huh? It's just like a table. You can use it to knock on it, but certainly not to do computations. Yeah, yeah, so that's the technical challenge. Huh? In principle, you know, we know how to do it. On paper is easy, yeah, but the engineering problem is very challenging. Yeah. And but the good thing is that, you know, in trying to solve that engineering problem, there are also science questions that pop up, yeah, that people can then solve, and you know, it goes hand in hand. Yeah, so that's there's been probably a revival of studies in foundational questions of quantum mechanics because of quantum computing. Yeah, because if you want to overcome certain engineering challenges, you end up discovering new science. Yeah, and so it goes hand in hand. Yeah. Sorry, I'm not keeping an eye on the Slack channel, so I don't know exactly if there were questions there, but I see we're already 5 minutes past 2. So thank you very much, everyone, for listening. And as I said, on Thursday, you will have an opportunity to learn and practice maybe a little bit of quantum computing on your own. Yeah. And Uwe, sorry, you just appeared. It's a clear sign that I have to disappear. So thank you, Uwe. All back to your lecture. Yeah.